Hello everyone, I am Moondra. I'm a PhD student at Georgia Tech. This work on fair facility location is joint with my advisors Swati Gupta and Mohit Singh. Let's get started. So as optimizers, the decisions we make using data given to us using our algorithms eventually affect human beings. Broadly, we are interested in the goal of making fair decisions using optimization. As an example of why this is needed, consider facility locations specifically. This is a map of mainland US depicting food deserts. These are low income and low access areas with no supermarket within a certain distance. They cover a large chunk of the total land area. What happens if new pharmacies are also open driven by profits? Will we see medical deserts in the future? So clearly, we want to be fairer to disadvantaged people, but fairness is not straightforward. Consider this example where we must decide the location of an emergency room given the location of some individuals. Most of them belong to the red group, while one of them belongs to the blue group. What should be our objective for placing the emergency room? One objective might be to minimize the individual's total distance or average distance to the emergency room. It seems reasonable, at least in this setting. But what happens if the blue individual is ghettoized away from the red group? Then the location of the emergency room moves far away from the blue individual with our previous total distance objective. One might argue that this isn't fair to the blue individual. To fix this, perhaps we can come up with a different, fairer objective. And of course, people have tried this, and many different fairness criteria have been proposed for facility location and related clustering problems. For example, this paper from as far back as 93 lists 20 different fairness criteria. Many more criteria have been proposed since. The trouble is that there is no agreement on what the right fairness criteria should be. Further, there is a trade off between different criteria, and it may not be possible to satisfy all of them simultaneously. Similar trade offs have been shown in machine learning, where it may be impossible to satisfy multiple fairness criteria simultaneously. So, how do we go about reconciling these various criteria? Let's look at an example of how this is done for organ donations. Consider kidney transplants at UNOS, which is a non-profit. Several people propose different policies, and one of those policies is then selected based on discussion and debate. The critical idea is to choose a set of candidate policies that represent different fairness criteria amongst a potentially infinite set of policies and fairness criteria. Note that a single fair policy is not decided in advance, but various stakeholders can comment on and choose from a portfolio of policies that incorporate different fairness trade offs. So, could we frame a corresponding optimization question to know if such representative small portfolios of good solutions exist? Formally, the optimization question is the following. We are given a set of solutions X and a class C of functions that represent our fairness criteria. For example, LP norms. Can we find a small set of solutions S such that optimizing any function C over X is equivalent to optimizing that function over S up to a factor alpha? That is, for each function f in the class, there should be some solution in S that is an alpha approximation for f over X. Let's look at an example. Here our domain X is simply line 2x plus y equals 30, or the points on that line, and our class of objective C is LP norms. Different points on the line are optimal for different LP norms. As the figure shows, the optimal L1 norm is on the x-axis, and the optimal L infinity norm is at 10, 10 on the line x equals y. If you only allow one solution in the portfolio S, then we could pick the L2 norm solution, and we can show that it will be a 1.2 approximation for all LP norms, including L1 and L infinity norms. This special case when one solution simultaneously approximates all objectives has been extensively studied. If we allow for two solutions, then we can pick the L1 and L infinity optima and improve the approximation ratio to 1.08. So clearly, to obtain better approximations, that is, decrease alpha, we need larger and larger portfolio sizes. So what does this trade-off look like between the approximation factor and the size of portfolio? This might get even harder to answer when x is a bunch of integer points or even a polytope. There are various issues. Even for a polytope, the optima for different functions may not even lie on the same facet. And then there's the question of what we can compute in polynomial time. This is distinct from the existence questions we have posed so far. We will put together these ideas to answer our question about reconciling various fairness criteria in facility location, which is the problem we are studying. Our class of fairness notions or objectives is LP norms. We will obtain a portfolio. We will obtain portfolios for these LP norms to avoid fixing a fairness notion. We look at the classic facility location problem. Here, we are given a set of clients D, a set of facilities F with opening costs C, and distances between all facilities and clients. The objective is to open some of these facilities and assign clients to open facilities to minimize the sum of the cost of opening these facilities and the distances of clients to their assigned facilities. The problem is well known to be NP hard and hard to approximate within factor 1.45. A 4 approximation was given by Schmois, Tardos, and Ardal in 97 and has been incrementally improved to 1.488. We will use the idea of client groups and LP norms to incorporate fairness into this model. Suppose we are given R client groups D1 through DR that partition the set of all clients. So each client belongs to exactly one client group. These could be based on relevant demographics. For example, for opening hospitals fairly, these might be based on gender, age, health insurance levels, etc. The goal, as before, is to open a set of facilities. However, instead of looking at individual client distances, we look at the average distance traveled by clients in a group. These are in pink, and then taking LP norm of these distances. The objective is to minimize the sum of cost of open facilities and the LP norm of these client distances. For higher P, the LP norm is dominated by the highest average distances for groups, thus prioritizing most distant groups over those close by. The first question is to solve this problem for a fixed P. Note that these LP norms are non-decreasing sublinear functions. And as one of our observations, we show that the 4 approximation of Schmois, Tardos, and Ardal works for all non-decreasing differentiable sublinear functions of client distances with only a polynomial number of oracle calls. This solves the problem for a fixed P. Let's go back to portfolios for all LP norms. So recall that we are looking for a small set of solutions such that for each LP norm, one of these solutions is a good approximation. In related work, Kumar and Kleinberg and Goel and Meyerson look at cardinality 1 portfolios for various problems. Golovin et al. Use the structure of LP norms and obtain portfolios for various problems. Goel and Meyerson's work essentially implies portfolios for clustering for a different class of objectives, top K norms. Our technique is closely related to that of Golovin et al. And Goel and Meyerson. Suppose we want constant factor approximate portfolios. We show that there exist 8 approximate portfolios of cardinality at most 1 plus log r to the base 2 for fair facility location with R client groups. Let's try to sketch the proof of the upper bound. Suppose we obtain 4 approximate solutions for each LP norm using the previous result. Let's call these 4 approximate solutions alg p for norm p. The first observation is that alg p is a non-increasing function of p. This follows from the non-increasing nature of LP norms. The second observation is that alg infinity is within factor r of alg1. Now, let's choose the norm p1 equals 1 with corresponding value alg1. Next, choose norm p2 such that alg p2 is exactly half of alg1. Similarly, choose p3 such that alg p3 is a quarter of alg1 and so on. Because alg infinity is within factor r of alg1, this can only be done log r times, and so the length of this sequence is at most log r to the base 2. The observation is that the 4 approximation corresponding to P1 is an 8 approximation for all P between P1 and P2. The 4 approximation corresponding to P2 is an 8 approximation for all P between P2 and P3, and so on. Therefore, solutions corresponding to these at most log R norms form an 8 approximate portfolio. That is the proof. The next question we consider is that of imposing some structure across solutions in this portfolio. The solutions in the portfolio may be unrelated and may not share structural properties. So, can we impose some structure? Aside from being a theoretically interesting question, this is also motivated by planning purposes and policy changes. Consider the recent Justice 40 initiative by the US government, which aims to set aside 40% of the budget for disadvantaged regions. However, it is not a one time investment, but rather will roll out in phases. As the initiative rolls out, more facilities will be opened in addition to already existing ones. This enforces a natural chain structure for facilities as they gradually roll out. Motivated by this, we consider refinements that model changes in norm P. As we discussed, the optimal value decreases as a function of P. Therefore, it is expected that the number of open facilities decreases. This leads to a natural constraint. As norm increases, a subset of facilities must be open. We can further demand structure on assignments. As norm increases and some facilities are closed, the clients assigned to these closed facilities must be reassigned. Consider this example. Suppose the facility in the middle is closed as the norm increases. Now, the 4 clients previously assigned to this facility must be reassigned to one of the open facilities. One possibility is that we could reassign each of them to their closest open facility, as in the picture. However, it might be administratively useful if all of them are reassigned to a single facility. Something like this. This also naturally induces a laminar family of sets based on the partition induced by assignments for different norms. Formally, a refinement is a portfolio of solutions that satisfies additional properties. First, open facilities FQ for a higher norm Q is a subset of open facilities FP for a lower norm P. That is, the facilities form a chain structure as the norm decreases from infinity to 1. Further, for each facility F in P, there should be a facility F prime in FQ such that all clients assigned to F under the assignment for P are assigned to F prime under the assignment for Q. That is that there is a subset structure with respect to assignments between F and F prime and the assignments for the two different norms. The quality of a portfolio is measured by its approximation factor, alpha, for every single norm. Note that this simultaneous approximation requirement is quite strong. It is not even clear if good refinements exist with all of these constraints. The problem of finding them algorithmically is a separate one. We show the existence of refinements with sub-polynomial approximation ratios, and we also find them in polynomial time. For arbitrary metrics, we give a poly r to the 1 over square root log r approximate refinement. Note that this interesting number is sub-exponential in log r, but also super polynomial in log r. For line metric, this approximation can be improved to order log r. Let's briefly go through the algorithm idea for arbitrary metrics. First, let's consider a natural greedy idea. For now, consider only two norms, L1 and L infinity. In the example, all 3 facilities are open for the L1 norm, but only the 2 red facilities are open for the L infinity norm. As a first step, assign each client to its closest facility in F1. This forms the assignment for L1 norm. Next, assign each facility in F1 to its nearest facility in F infinity. The 2 red facilities are already open in F infinity, but the yellow facility is assigned to the right red facility. As the norm increases and the yellow facility is closed, the 4 clients assigned to it are reassigned by following the arrows, and so they are assigned to the right red facility. This forms the assignment for the L infinity norm. It can be seen that these facilities and assignments formed this way form a refinement. But this could lead to a client being assigned far away for some norms. Consider this example on a line with a client at x equals 0. Recall that we have a portfolio of 1 plus log r norms. Call this number t and consider facility sets f1 through ft corresponding to these norms. The greedy algorithm first assigns the client to the facility at x equals 1 in f1. This facility itself is then assigned to facility in f2 at x equals 3 and so on. So for ft, this client is assigned to a facility at distance 2 to the t minus 1 when a nearby facility at minus 1 plus epsilon in blue there existed. The smarter strategy is to look beyond f1 when assigning the client. Consider the closest facility for each fk. Notice that the facility at minus 1 plus epsilon is closer to the client for the facility sets f2, f3 through ft than any other facility. Now, discount for distances at higher k, shrinking them by a factor gamma to the k. That is, the facility in fk, that is, the corresponding distance is divided by gamma to the k for some parameter gamma greater than 1 that we will fix later. Choose the discounted closest facility. In this case, it's the facility ft. For each of f1 through ft, assign the client to this facility. At least in this case, we can see that this forms a refinement for this client. Let's consider a more general setting. Again, fix a client. Look at the facility closest to this client for each k in 1 through t. Call these facilities small f1 through ft with corresponding distances d1 through dt as in the picture. Now discount larger distances using discounting factors. That is, the distance dk is divided by gamma to the k for some parameter gamma greater than 1. Select the facility fk with the least discounted distance. In this case, it's the facility f3. For facility sets f1, f2, and f3, assign the client to the facility small f3. For f4 through ft, we do a recursion where we treat this facility small f3 as a client. So it takes some work to formalize this and show that it indeed forms a refinement. The detailed algorithm and its analysis is in the full paper. Of course, we still need to choose the parameter gamma. Choosing gamma equals 1 basically recovers the greedy algorithm since d1 is the smallest distance and the algorithm chooses the facility in f1 in this case. Therefore, choosing small gamma can lead to an exponential in t approximation ratio. Choosing large gamma also leads to exponential approximation ratio. We show that choosing optimal gamma gives an exponential in square root t approximation ratio. In terms of t, this is polynomial in r to the 1 over square root log r. In summary, we looked at the issue of various equity notions for facility location. We specifically considered LP norms as a class of fairness notions. We showed extension of an earlier algorithm to any fixed LP norm. We considered small portfolio of good solutions for all LP norms and gave an 8 approximate portfolio of size 1 plus log r for R client groups. And while we did not discuss it, the full paper gives a roughly square root log r lower bound on sizes of such portfolios. Next, we considered imposing structure across solutions in this portfolio, which is motivated by policy considerations, and we introduced the notion of refinement. We gave poly r to the 1 over square root log r approximate refinement for general metrics. A natural question that arises from this work is whether the class of LP norm objectives is the right class of fairness criteria. In future work, we consider more general classes of objectives such as ordered norms and symmetric norms. Thank you for your attention.